Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate level physics questions. So here's our first one. I'll just read it off. So we have a wire that's 1.60 meters in length. And it carries a current of 32.3 milliamps. And the whole wire can be arranged as a single loop in a circle shape, a square shape, or an equilateral triangle. And we can make the whole thing into a compact coil with end turns. We're asked to calculate the magnetic moments in each case. So the magnetic moment is defined as through the torque, which is exerted in the presence of an external magnetic field, where the mu vector I show here is the magnetic moment. And so the way you can define the magnetic moment is by basically expanding what you would expect the torque to be and getting it into this form, and then what comes out is the magnetic moment. Now for symmetric shapes like this, our magnetic moment is going to come out to be IA. In this case, actually, IA, and then we would use the right-hand rule to define the magnetic moment. And so I'm just going to call it K hat, where if I have, say, a circle with current running clockwise, let's actually go with current running counterclockwise. So my fingers would curl around, then my magnetic moment would go out, straight up. Right, so fingers curl around. And so then my thumb would point in the direction of the magnetic moment. Quite scary looking hand, but I think that's kind of explanation. And I'm just gonna erase that because it kind of scares me. All right, but our magnitude of our magnetic moment, which I'm just going to call mu from now on, is just IA. Okay, so for a single turn circle, then our length is 1.60 meters. The length of a circle is its circumference, so 2 pi r is equal to 1.60 meters. So then r is equal to 1.60 over 2 pi. And so then its area is pi r squared, which is equal to pi times 1.60 meters over 2 pi squared. Which, if we do it all out, comes to be 0.204 meters squared. So that's magnetic moment for a wire which carries 32 times 10 to the minus 3 amps times this area. is 6.58 times 10 to the minus 3 amp meters squared. So that's for our circle. And then for our square, our square is going to be, each side will be length L. And so our circumference is going to be 4L, which is equal to our total length, which is this case 1.60 meters. So L is 1.60 over 4. And so our area is L squared for a square, which is 1.60 meters over 4 squared, which is 0.16 meters squared. And so then our magnetic moment is 32 times 10 to the minus 3 amps times our area, which comes out to be 3.986 times 10 to the minus 3 amp meters squared. So that's for a square. And then for equilateral triangle, oops, oh, that was a mistake there. So our equilateral triangle is going to have each side of length L, and our area is going to be 1/2 the base times the height, or the height times the base, as I've written it in here. And so it's an equilateral triangle, meaning each of these are 60 degrees. So our height here is, I guess I might as well do it this way. So then the sine of 60 degrees is our height over our length, or our height is sine 60 times our length, which is √3 over 2 times our length. And just to make that slightly more clear, it's square root of 3 over 2 times our length. So our area is √3 over 4 L squared, which is √3 over 4 times our, so our length, and now for our circumference here, so our 3 times our L is the 1.60 meters. So L is 1.60 meters over 3. So then this is 1.60 meters over 3 squared. And if we do that all out, it comes to 0.1234 meters squared. And so then our magnetic moment is 32 times, I dropped it here, sorry. 32.3 times 10 to the minus 3 amps times our area, which comes to be 3. Oh, alright. Okay, gotta be slightly more careful with how I write here, sorry. So this here actually comes to 5.168, sorry, 5.168 times 10 to the minus 3 amp meter squared. And this one here actually comes to the 3.986. Sorry about that. There we go. All right. And then for a circular loop with n turns, so we have a circle, put that with multiple turns. Our area is still going to be pi r squared, but n times our length, or sorry, but our length now is the 1.60 meters, which is going to be n, so our number of turns times 2 pi r, where r is our radius for our circle, n is our number of turns, and so we have n of our circumferences. So then r is 1.60 meters over n 2 pi. So then our area is pi r squared, so 1.60 over n 2 pi squared. And so then our moment is our current, 32.3 times 10 to the minus 3 amps times our area, which comes out to be 0.204 meters squared over n squared. And so then it's pretty much it's the same as the circle. Amp meter squared, but over n squared. There. Okay. So then, and I'll just circle that one. So there's for our coil, it then turns. All right, so then if we scroll up here and just check the solution with what was given. All right, so when the wire is a circular loop, we get an area of 0.203, 204, so that's just rounding differences. Our magnetic moment looks to me like they're missing a 10 to the minus 3, but that's okay. That's for n turns, so they just skipped ahead. They're also missing the n squared. So this one actually has, for the square loop, it looks like they made the same mistake as I did, but jumping ahead. So where's their area? Well, squared over 16, 1.6. So if they actually did the calculation shown there, that would be off, because this is the magnetic moment I believe I get. So I think they're just wrong there. And The equilateral triangle looks right. I might just double check their math though with the second one just to be sure. So 32.3 times 10 to the minus 3 times 0.16 is the 5.168. And then if I do theirs, yeah, so that's where, so they missed the L squared in this for the square. Okay, so I'm just going to say for A, they missed 1 times 10 to the minus 3. For B, missed L squared. Okay, and so it's basically just small mistakes, but I'm still going to just mark it as incorrect so it can be corrected. Okay, so here's the second question. A cyclotron is designed to accelerate protons. So we're going to start at rest near the center, and it's going to spiral out. If I can draw the spiral with an outer radius of 0.330 meters, and they're emitted nearly at rest from a source at the center. And each revolution, so each period, is a delta V of 600 volts. Or maybe I'll write this. Each delta T goes through delta V of 600 volts. And then we've got a B field of 0.550 Tesla, which is keeping our proton rotating. So the B field must be out of the page. So if we put from our right-hand rule, if our proton is moving to the right, QV, and our B field is out of the page, then our force is QV cross B. Now this doesn't matter too much for what I've drawn here, other than just for consistency. Then our force would be, put our fingers in the direction of the QV, our palm in the direction of the B field, and then our thumb would point in the direction of the force. So our fingers in the direction of QV, our palm in the direction of the B field, and then our thumb points in the direction of the force. So that's what's giving us our circular motion. In this case, I drew it this way, and if it was wrong, then the spiral would just be the other way. But it looks like I drew it the right way, so it's attempting to go in a circular motion, but then each cycle, we're pushing the kinetic energy higher, which is pushing the circle outwards. So I suppose it actually should be drawn something more like this. Which I can't do, but the maximum radius is 0.330 meters. So our force is QVB. I've gotten rid of the cross product because they're perpendicular to each other, so it's just going to be QVB. And I've also gotten rid of the vector notation because the magnitude of the force is going to be our centripetal force. So it's going to give rise to our mv squared over r for our motion. Which we can then use or solve for our velocity for a proton by rearranging for the velocity. So first we can cancel this velocity and cancel the square, and then we can rearrange to say that QB over M is equal to V over R. And I left the R on this side because our omega is V over R, so that's our angular frequency, or QB over M is equal to omega. So then each period we go through a delta V. Let's just run through the answers to the question. So that is our cyclotron frequency. So that's our frequency for our motion. So that's how we are going to get it. So for A, omega is the charge of an electron, 1.6022, charge on a proton, which is just the positive of the charge of an electron. So 1.6022, 10 to the minus 19 coulombs, times B, 0.550 Tesla, over the mass of a proton, 1.672622 times 10 to the minus 27 kilograms, which is 52.684, 10 to the 6, 1 over seconds. So there's our cyclotron frequency. Find the speed at which the protons exit the cyclotron. So V is omega r. So omega is not going to change as as it goes around and around. It's still going to have the same cyclotron frequency because the charge, the B field, and the mass are constant. The only thing that's going to change is the radius at which it orbits. And at the maximum radius, our max is given as 0.330 meters. So our V at maximum is 52.684 times 10 to the 6, 1 over seconds, times this 0.330 meters, which is 17 times 10 to the 6 meters per second, which is very high, right? So it's, remember, the speed of light is 3 times 10 to the 8. So this isn't quite there, but it's getting close. So then C, find their maximum kinetic energy. So kinetic energy at max would be 1/2 the mass of a proton times our Vmax squared. So mass of a proton is this 672,622 times 10 to the minus 37 kilograms times our speed at max squared. And that equals 2.528 times 10 to the minus 13 joules. And then just converting it to EV, which is kind of a nicer unit when dealing with these kinds of units, which is the conversion factor is just the charge on an electron in joules per EV. So our joules are going to cancel, leaving us with EV 1.578 times 10 to the 6 EV, which is about 1.6 mega EV. And that's also just as you go on with your physics learning, you'll start to figure out kind of ranges of things. And I think a cyclotron, which gives you an energy of about in the mega EV range, sounds about right. So that looks like we're doing things correctly. A lot of times that's a good way to check that you're not making any mistakes. Okay, so how many revolutions does a proton make in the cyclotron? So we know that our delta KE is 600 volts per revolution, right? So we said for each period, we go up by 600 volts. And we can convert this to EV by, our delta V, I should say. And we can convert this to a delta KE by multiplying by charge. So 600 volts per revolution times the charge on a proton. And then we can convert it to EV by dividing by the factor, which is just the charge, the charge on an electron, which is the same as the charge on a proton. So those are going to cancel, except for the coulomb. And a coulomb volt is a joule, so then the joules will cancel, and we're going to be left with 600 EV per revolution, which makes our conversion to, when we convert it to EV, that's going to make this significantly easier. So then if our KE max, if our KE initial is 0, and our KE final is 1.578 times 10 to the 6 EV, and we have a delta KE is 600 EV per revolution, then the number of revolutions is just our 1.578 times 10 to the 6 EV minus 0, minus our initial, which is just 0. So I might as well just include it just for fun, over our 600 EV per revolution. Now, revolution isn't really a real unit, but I'm just keeping it around just so that we can work with it kind of to calculate our number of revolutions. And so we see that the EVs will cancel, and we'll have revolution upstairs. So that kind of means that this little equation is correct. And so if we do this math, it comes out to 2629.6 revolutions, or 2629 full revolutions. So we'll get through 2629 full revolutions. Okay. And now for what full time interval does a proton accelerate? So our omega is 52.684 times 10 to the 6 rads per second. Again, rad isn't a real unit, but it sometimes helps to differentiate. Our period is 2 pi over omega, which is 2 pi over our 52.684 times 10 to the 6 per second, which is 1.193 times 10 to the minus 7. And this is in seconds per revolution. Again, revolution not a real unit, but just to keep kind of track of things. So if we have 29.6 revolutions, then our full time will be our 29.6 times our period per revolution, so 1.193 times 10 to the minus 7 seconds. Okay, and so that comes out to be 3.1361 times 10 to the minus 4 seconds. So then that's our that's the time that a proton spends in the cyclotron. Okay. So now going through each of these. So here's our frequency, 5.26 times 10 to the 7. So I've got 52 times 10 to the 6, so those are really the same. And I've kept quite a few digits. Obviously, it should only be 3 digits for significant figures. And then the rest is just rounding differences. Our velocities are the same. Again, I should only have 3 digits for significant figures, but that's okay. C, our KE max, 1.58 times 10 to the 6, 1.56, so I'd say that's probably, again, rounding differences. During the time interval t over 2, the energy of the proton increases by, I must have misunderstood perhaps. The protons are from a source at the center. Each time they cross the gap between the D's are between the poles. Oh, I see. So that was my mistake. So it should have been like this. I see. So then delta KE is, delta V, delta V is 600 volts here, and delta V is 600 volts here. So it actually increases the kinetic energy twice in a revolution. So I'm doing it for once per revolution. Okay, so then my delta V should be 2 times 600 volts per revolution. So then this should be 2 times this, so then 1200 EV then per revolution, which significantly changes things. So again, 1200 EV per revolution. So then the number of revolutions here actually halves. giving me, I'm just going to do this here. So my apologies here. So it should be just 29.6 divided by 2. So this actually should be 1314.8 or 1314 full revolutions. And then the time spent will just be this value times our 2 pi and divided by our frequency, which is 52.684 times 10 to the 6. So then our our time in will actually just be 1.568 times 10 to the minus 4 seconds. Not these values. All it really does is have everything, because I was doing the calculations for one, and I apologize for that. Here though, so that's not correct. It's not, we needed to divide by the conversion factor to EV, which was a mistake there, which makes the revolutions quite significant there. And then obviously that's going to carry forward to there. So let's say demist conversion to EV. Mistake carries forward to E. Should be D is about 1314.8 revolutions, and E is 1.568 times 10 to the minus 4 seconds. Okay. So I'll just say it's incorrect just because of those small errors, just so it gets corrected. But it's basically correct, just small errors. Okay. So we have a region of space. So for this question, we have a region of space near the Earth's surface, below which we have no B fields, so we've got some y equals 0, and above that we have a B field going into the page, and we've got a wire loop which we are dropping. Now the wire loop is a square wire loop with resistivity rho, mass density. I'm just writing these out because they decided to call them rho m and rho, so that could be a little confusing. And then the diameter of the wire is given as d. D equals d. That's good. Diameter equals d. So if I take a cross section and draw it out, then it has a diameter of d, and the side length is L. Okay, so A is an easy one to answer. So while the loop is perfectly immersed in the magnetic field as it falls, determine the drag force when, on it at the moment when its speed is v. So, so the force due to the magnetic field is Q, so I'm just going to call this F mag, is QV cross B. So that's for a charge with a velocity v. Now this can be rewritten as I dx cross b. And so if we have a current, now to figure out what current is going to be flowing, we would need our EMF. So our EMF is going to be minus d phi by dt, where phi is our flux. So our phi is B dot A. Okay. And so in this case, when it's fully immersed in the field, then we have our B field, which is constant and into the page. Our area is just L squared, so BL squared. And so then our EMF is minus d phi by dt, which none of these depend on time, so it's 0. And so then if our EMF is 0, then our EMF is equal to our current times our resistance, so then our current is 0. So we have no current flowing when it's fully in the field because nothing's changing. And so because we have no current flowing, then our magnetic force is 0. Okay. Now, now that we have that, if we now, while the loop is perfectly immersed as it falls into the zero field region, determine the drag force when its speed is v. So I think I maybe I'm just gonna do it for I'm just gonna do the drag force while as it comes out of the zero field region. So our F mag is 0 up until up until it essentially reaches this point. And then as we start to move in, so as we start to move the loop into the zero field region, that's when things start to happen. Okay. And so now our phi is still B dot A. But our A is now just the area enclosed by the B field. So it's L on this side, but then on this side it is, and we're going to give it a speed v. So it's falling with a speed v, which is changing with time due to its acceleration. But it's falling with a speed v. And so this length here is actually L minus v delta t, or v dt, if you will. Or even better, just to make everything seem more reasonable, L minus vt. Right, so that distance is L minus vt. Now we're assuming that we're starting at time equals 0 when it's right at the y equals 0 point. Okay. So then our phi with this expression is then b, as our b field's constant and parallel to our a field. Then our area is L times L minus Vt, like that. And so then our EMF is minus d phi by dt, which is going to give us B, L, V, just BLV, right? Because this is B times L squared minus LVT. Okay, and then the derivative of this with time, this part's not going to depend on time, and then this part does. So we're just left with a BLV. Okay, and our current, or our EMF, is positive, meaning that is our flow of positive charge, or our current, is going to be that way around the loop. We can double check this with some of the rules we know, as we know that our force is going to be I dx cross B. So we can use the right-hand rule. So if our current is running to the right from the top, and we put our palm in the direction, so we put our fingers in the direction of the current, and our palm in the direction of the magnetic field. So our fingers in the direction of positive current, so flow of positive charge. Our fingers in the direction of the flow of positive charge. Our thumb in the direction of the B field. Then our thumb points in the direction of the force, so the force will be upwards. And we know that the current generated will be to oppose the motion, and this indeed imposes the motion of it leaving the B field, and so that makes sense. So our direction that we get here makes sense, and yeah, so that all looks good. We can solve for our current by saying that it's the EMF over the resistance. We can calculate our resistance for our wire from our resistivity by the length of the wire times the resistivity over the area, our cross-sectional area. So our length is 4L, our resistivity is given as rho, and our cross-sectional area is going to be pi r squared. Now our radius can be computed from our diameter over 2, as we're given the diameter for our wire, or we're given that we know the diameter d. So it'll be 4L rho over pi d squared over 4, which is just 16L rho over pi d squared. And these are in terms of constants that were given in the question. So now we can plug in some of our values here. So our current is going to be BLV over 16L rho over pi d squared. We can cancel these L's and bring the pi d squared up top. So BV pi d squared over 16 rho. And so then there is our current. Okay. So that's our current given a velocity v. And so then our force, which so our force on some dx I've given as I dxb in this direction. So our total, so that's a small increment of force. So our total force will be the integral. Now if we look at the current just from the top, or if we look at the force just along the top, then we're going to integrate over the length. So our force is just going to be IBL, so we're just integrating over that length. If we look at this length here, well then our current is going down. We use our right hand rule, so the force will be outward this way. So we do have a force in that direction, but it's perpendicular. And if we look at this side where our current is flowing this way and use our right hand rule, then we'll see that the force is going in the opposite direction. So these two actually cancel, and then there's no force on the bottom of the loop. So in other words, we only need to consider the force at the top of the loop, as that is going to be our only contributor. So that is our magnetic force, just IBL. So then plugging in our our value for the current that we just calculated, so BV pi d squared over 16 rho times B times L, or B squared V pi d squared L over 16 rho. And so then that's our magnetic force. And okay, so then and so that's our magnetic force. So that's our full answer to A. There. Okay, and now if we look, so when we're looking for a terminal velocity now, so we've got our loop falling with some velocity v. We look at our forces, we have mg and F mag. So our F net is B squared V pi d squared L over 16 rho minus mg. And in fact, this equals ma. Our terminal velocity is when ma equals 0. So when b squared v pi d squared L over 16 rho minus mg equals 0. And so we want to solve for our terminal velocity vt. So first of all, we were told that our mass, that we have a linear mass density rho, or sorry, not a linear mass density, but a mass density rho. So our mass is going to be our length of our wire times our cross-sectional area, which we're given d's, diameters, so cross-sectional, still got a cross-sectional area, but we're given the d, so d over squared, d over 2 squared. Just rewrite that to be a little bit clearer. Times our linear mass, our mass density, not our linear mass density, but just our mass density. And so then our length is 4L times pi d squared over 4 rho m. So the 4's will cancel. So pi L d squared rho m. So that's our mass. And so then we're just going to use that in this expression above and solve for our terminal velocity. So first, moving things to either side of the equation. And then we can cancel the pi, cancel the d squared, cancel the L. And then solve for our terminal velocity. So Vt is equal to g over b squared times 16 times our resistivity times our mass density. And just to be sure that I didn't make a mistake there, okay, there it is. Yep, so that looks good. So there's our terminal velocity in terms of the values we're given. Okay, and then so C is find our terminal velocity if it's made of copper and our B field is 0.80 Tesla. So if we're made of copper, then we can look up these values and find that our mass density is 8.96 grams per centimeters cubed, which we can convert to kilograms. And convert our centimeters to meters, so 1 times 10 to the 2 centimeters per meters cubed. And we get a mass density of 8,960 kilograms per meters cubed. And we can look up our resistivity for copper, which is 1.68 times 10 to the minus 8 ohm meters. Okay, yep. And so then our terminal velocity is 9.8 meters per second squared over our B field, 0.80 Tesla, times 16 times our mass density, resistivity, 1.68 ohm, 1.68 times 10 to the minus 8 ohm meters. And so the value comes out to be this should be b squared, so that's squared. 0.0369, and this would be in, if we're following along here, ohms. Looks like ohms, kilograms, meters squared per Tesla squared, seconds squared, meters cubed. So the meters squared will cancel there. This here, a Tesla is a kilogram per coulomb second. A ohm is a kilogram meters squared per second coulomb. Might be seconds. Coulomb squared. Yeah, coulomb squared. So then, yeah, okay. So then this is in 0.0369 kilogram meters squared per second coulomb squared times kilogram per second squared meters times coulomb squared second squared per kilogram squared. So this is the ohm unit. This is what's left, and this is the Tesla squared unit. And so we can see that the coulomb squared will cancel, the second squared will cancel, the kilograms squared will cancel, and the meter will cancel, leaving us with 0.0369 meters per second. All right, so just a quick unit analysis to make sure we didn't make any mistakes. So it doesn't look like we did since the units all work out. But let's check our solution with what's given here. And so there's our induced EMF. And so there's our resistivity. There's our current. Our dA dt is just LV. And so the current is going to be BV pi d squared over 16 rho. They just didn't cancel the L, so that's okay. And so then we get an L up top. So there's our magnetic force. So again, that looks okay. Our magnetic force is going to equal our mg. So our terminal velocity is, so that looks good. And then using values that we look up, 8960, so that's about the same, 1.68 10 to the minus 8, so that's good. And it comes out to be 0.037, so yep, that looks pretty good. All right, so we'll say solution is correct. Looks good. All right, so for the fourth one here, an electron in J.J. Thomson's E over M apparatus moves perpendicular to a B field. So we've got our B field into the page, say, and we have an electron moving this way. And now using our right-hand rule, our force is QV cross B. And remember, for our right-hand rule, we have to put our fingers in the direction of positive current flow or positive direction. Or we just need to invert it. So if we put our fingers in the direction of the velocity, our palm in the in the direction of the B field, then our force is in our thumb is pointing in our force direction. But in this case, because we're talking about an electron, we have to invert the force, so the force is actually going to be downward. So not according to right-hand rule, but that's because Q is minus E. Okay, so for an electron, we have to point the force in the opposite direction. Okay, that's not super necessary for this question, but just an aside. So our force is QV cross B, which, as they're perpendicular, can be just written as QVB. So it's moving currently, it initially is moving with a radius of 10.4 centimeters. So this is our centripetal force, so mv squared over r. And so we can readily solve this for our velocity. And then, so what we have, and then we add an E field and it makes the path straight. So we've got it moving in some circular path, and then we add an E field, which in retrospect, I'd have to make the E field this way, which makes the path of the electron straight. As the B field is going to want to continue to make it go in a circular motion, but the E field is going to oppose it. So that's a magnetic force, while our electric force is just QE. All right, and so for it to fly straight, our QVB minus our QE must equal 0. As for it to fly straight, there's no longer centripetal acceleration, or QVB is equal to QE, or our, what is the value of B? So B is E over V. Okay. So our velocity, we can use this above expression to solve for our velocity. So cancel the V here. Our velocity is just QBR over M. And so then our B field is just E over Q BR over M, which we can bring this B over to this side and say B squared is ME over QR. And so then we're given our radius, we're given it's an electron, and we're given that the E field, and we're given the E field. In this case, we've already kind of taken into account the charge on the electron in all of this. Or at least here we have actually. So in retrospect, I should have written this as E and E here, not Q. And so in retrospect, this should have been E. Not that it makes a whole lot of difference, but we would end up with a negative in our square root, which wouldn't be so kind. And so then B squared is our mass for an electron, 9.11 times 10 to the minus 31 kilograms, times our E field, which is 18.10 times 10 to the 3. And a volt per meter is just a Newton per coulomb. But I might as well, I guess, leave it in volt per meter. I don't know why I converted it. Charge an electron is 1.6022 times 10 to the minus 19 coulombs. And the radius was given as 10.4 centimeters, so 0.1040 meters. And so our B is actually the square root of all of these. And so our B is 9.948 times 10 to the minus 4. And if we do work out the units there, it will be Tesla. And so that's our B field. And so suppose our E field measurement has an uncertainty of 0.750 kilovolts per meter, and our radius has an uncertainty of 0.1. What is the total uncertainty associated with the B field? Okay, so if we represent our B field as, or if we represent our B squared as ME over ER, and our mass and our electric charge don't have any uncertainty, then we can compute our uncertainty through just differentials. So this will give us 2B dB is equal to M dE over ER plus ME over ER squared del R. Where although the derivative of 1 over R would be minus 1 over R squared, the del R is plus or minus. So we're obviously going to take whichever will give us the larger error, as we want to know our maximum uncertainty here. But B squared is, so in this case, B squared is ME over ER, or E is, how to write this, ER B squared over M, or ER over M is E over B squared. So we can put that in there, and in fact we can also use that over here. So we see that we have, so this is just B over R, and this is just b squared over e. Okay. And so then, oh, sorry, this is b squared over r. There you go. That makes more sense. Okay. So then we have 2b del b is b del e over e plus b squared del r over r, dividing through by b squared, or sorry, dividing through by the 2b on this side. Then our del b is just b over 2 times del e over e plus b over 2 del r over r. And so then we have our b field, which is just, so 1/2. Our b field was calculated as 9.948 times 10 to the minus 4 Tesla. Our error in our E field is given as 750, just 750 volts per meter, so it's 0.750 kilovolts, but I just converted it over 18.10 times 10 to the 3 volts per meter. And our uncertainty is given as 0.1 centimeters, so 0.001 meters over 0.104 meters. And if we do this out, it comes to 2.539 times 10 to the minus 5 Tesla. Okay. And, okay, so now checking through our solution here. So our B field comes out to be 9.948 times 10 to the minus 4, so it's, or 0.9 times 10 to the minus 3, so that's the same. The last digit is a little different, but that would just be rounding differences. And the uncertainty in our field comes out to be significantly different. Oh, but they have a different B field here. That's kind of odd. Yeah, they use a different B field for this calculation, so that's just odd. I don't know why that would be the case. Did the question give it? Nope. So I have nothing there for why that would be the case. So in any case, that's the reason why that's going to be different. And this is just the solution. Oh, here it is down here, 2.54. Yeah, so okay. So it is the same. They just, in their summary, gave a different one for some reason. Okay, so that looks good. All right, so that looks good. All right. So now for, this is only the 5th one. So we have a conducting loop in the shape of a rectangle, and it moves to the right. And we've got a B field. So we've got our conducting loop moving with some velocity. And we've got a B field going into the page. Of 0.06 Tesla. And so it asks, first of all, when the loop is still entirely within the region, what is the magnitude and direction of the current flow? So our EMF is minus derivative of the flux with time. Our flux is B dot A. So when it's completely within the, immersed in the region, then our area, which is given as 5 centimeters by 2 centimeters. So nothing's changing though. So our B dot A is just our B field times our area. And so then our flux, our EMF, is the minus the derivative of our B times our area with time. And so then it equals 0. And so our current, which is our EMF over our resistance, is equal to 0. So when it's fully immersed in the field, we have no current. And then, so for B, when it's moving out of the field, so now we've got our B field, and we're moving out of the field with velocity V. This is 2 centimeters. And now all that matters is the area that's within the field, which is going to be our full length minus our velocity times time. So then our area is 2 centimeters times our 5 centimeters minus our velocity times time, which is equal to 10 centimeters squared minus 2 centimeters times velocity time. So then our flux, which is our B field dotted with our area, is going to be B times 10 centimeters squared minus 2 centimeters times our velocity time. Our EMF, which is minus d phi by dt, is going to be the derivative of this expression with time. And as we can see, this part doesn't depend on time, so it's going to go to 0. And then the derivative of time here is going to leave us with B. The minuses will cancel, so B times 2 centimeters times velocity. We can actually calculate our value now. So our EMF is going to be 0.06 Tesla. We can convert our 2 centimeters to meters, so 0.02 meters times our velocity, which is given in the question as 60 meters per second. And so 0.06, is that right? Oh, it's 0.06 Tesla. For some reason, I did all my calculations with 0.05, which... Okay, well, gives us, so 12, and I'm just going to have to recalculate a bit, I guess. .072. So that's 0.72 volts. And so then the question says the resistance of the wire is 5 ohms. So from Ohm's law, we have that our current is our EMF over our resistance. So 0.072 volts over our resistance, which is 5 ohms, which comes out to be 0.0144 amps. Okay. And so then there's our current. The direction of positive current will be clockwise around the loop. So that EMF will give us a clockwise positive current, which makes sense if we use our right-hand rule. Point our fingers in the direction of the current, at least on this loop here, and our palm facing the direction of the B field, and our thumb will point in the direction of the force. We know the direction of the force should oppose the change in flux, so should try to move it back into the B field. And so our net force is going to be to the left. So that makes sense. Okay. And so our EMF is 0.072 volts, and our current is 14.4, and the direction of positive current will be in the clockwise direction. So that looks good. So that's correct. This one's a pretty quick one, so I'm going to run through this one as well. All right, so we've got two spheres, and we're going to treat them as if they're right next to each other. And we release them from rest. One sphere has a mass of 2 grams, the other a mass of 1 gram. Both have a diameter of 2.2 millimeters, so this is 2.2 millimeters over 2. This is 2.2 millimeters over 2. So their distance between their centers is 2.2 millimeters, which is 2.2 times 10 to the minus 3 meters. The charge on this guy is 2.0 nanocoulombs, and the charge on this guy is 1.0 nanocoulomb. And it wants to know what their speeds are when they're very far apart. So we can compute the potential energy when they're next to each other as 1 over 4 pi epsilon naught QA QB over R, which, as they both have the same sign charge, is going to be positive. So we've got 2.0 times 10 to the minus 9 coulombs, 1.0 times 10 to the minus 9 coulombs over 4 pi. Epsilon naught is a constant in coulomb squared per meters joules, and R is 2.2 times 10 to the minus 3 meters. And this comes out to be 8.1705 times 10 to the minus 6 joules. Now, when the particles are very far apart, R goes to infinity, so U goes to 0. So, we're going to have a kinetic energy of KE. So then delta KE is equal to delta U from conservation of energy. So then our delta KE is actually going to be minus delta U, which is, and our initial kinetic energy was 0, so KEF minus KEI is equal to minus UF minus UI. Our UF is 0. And so then our final kinetic energy is just our initial potential energy, which is this 8.1705 times 10 to the minus 6 joules. Our kinetic energy final is 1/2 mVA squared plus 1/2 m, I should have put A's on everything, VB squared, which is equal to this 8.1705 times 10 to the minus 6 joules. So we also have conservation of momentum. And our momentum initially was 0 as nothing was moving. And then our final momentum is MA VA plus MB VB. And so PF equals PI. So then this equals 0. And so then we can solve for VB by saying that VB is minus MA VA over MP. Or for use in our kinetic energy expression, we can say that VB squared is MA squared VA squared over MB squared. Plugging this into our kinetic energy, we have 1/2 MA VA squared plus 1/2 MB VA squared MA squared VA squared over MB squared is equal to this 8.1705 times 10 to the minus 6 joules. So we can cancel one of these MBs and say that 1/2 MA VA squared onto 1 plus MA over MB is equal to 8.1705 times 10 to the minus 6 joules, or VA squared, or VA is the square root of 2 times 8.1705 times 10 to the minus 6 joules, all over our A mass, which is 2 times 10 to the minus 3 kilograms. So converting it from grams into kilograms, onto 1 plus 2 times 10 to the minus 3 kilograms over 1 times 10 to the minus 3 kilograms. And the square root of all that. If we do this on our calculator, we get 0.05219 meters per second. Our VA is obviously going to be to the left, and this is our magnitude of our VA, or just our speed. So I'm going to say that VA is minus 0.05219 meters per second, just to match up with the figure. And then VB is minus, from our momentum expression, our mass of A over our mass of B times the VA we just calculated, so minus 0.05219 meters per second which comes out to be 0.10437. Okay, so if we check our solution here, so first computer potential energy when they're next to each other, so 8.18 times 10 to the minus 6, so 8.17, 8.18, just different by rounding. We can use our kinetic energy expression and our conservation of momentum to get that our VB is 10.4 times 10 to the minus 2, so that's that, and 5.2 times 10 to the minus 2, so that's that. So that looks the same, so that looks good, solution is correct. All right, and then I'm actually just going to stop it there and say that's it for today. If you enjoyed this, please subscribe to OneClass. If you want to leave questions, please follow the links below the video. This has been Jeff Krause for OneClass.